Okay, let's see, share file. Oops. Okay, this is where we stopped last week. So we talked about the nomenclature, which I will really recommend some of you to. I will really recommend you guys to know some of these names. Okay, because sometimes I will only refer to this compound by their names, and then I expect you guys to be able to draw the structure in your head. Remember, if you can't draw the structures, it becomes difficult for you to answer the question. So, generally, whenever you see the term aryl being used, hmm, whenever we see the term aryl being used, we simply refer to a benzene ring, okay, or the benzene acting as a substituent. So, for example, phenol, this is phenol here, will sometimes be referred to as aryl alcohol. That's where phenol can sometimes be referred to. And the short form of it can be abbreviated as AROH because the AR stands for aryl. Okay, and remember, pH also. pH stands for phenyl. We've talked about it last time. And BZ stands for benzyl. Okay, the phenyl group correspond to this group here, whereas the benzyl group correspond to that group over there. Okay, so that's good for us to remember. Okay, now if we want to do the nomenclature of this molecule here, if you want to name that molecule, the parent group, the parent name would be this. That's our parent name. Okay, and that parent name is simply phenol. So that is a phenol. That's our parent name. And so we need to now name the bromine with respect to the phenol. This carbon where the OH is connected is the highest priority. It's always carbon number 1. That's why it's called phenol. And so bromine is carbon number 2. So this will be called 2-bromophenol. That's how that molecule will be named. And we can use the same reasoning to name this other molecule. So we have the parent molecule over there. So the parent molecule also will be called phenol. And this is carbon number 1. That will be carbon number 2. And this is carbon number 3. Okay. Remember, you always choose the direction that will give you the smallest number. Okay. And so for carbon number 1, 2, and 3, this will be called 3-ethyl phenol. That will be the name of the molecule. Does that make sense, guys? And I think sometime we'll be able to go into more detail about the nomenclature of a di-substituted benzene in subsequent slides. Now, the next thing we have to do here, and which is the main objective of today's class, we'll be looking at the different reactions of benzene. And that will be my point of focus. I want you guys to be able to know all those reactions. Okay. And generally, aromatic system or benzene react following a mechanism called electrophilic aromatic substitution. That's the mechanism, that's the name given to the reaction. And if you guys remember, we always said in class that names in organic chemistry are usually descriptive. So they describe what is actually happening, they describe the situation. In this case, it is an electrophile that is undergoing a substitution. Okay, so this is the opposite of what we've seen before in the past. If you remember, in the past we've talked about XN reaction, which was a nucleophile acting as a substituent. So nucleophilic substitution, that's what we did in the past. But here now we're looking at an electrophile acting as a substitute. And so this is the general reaction scheme for electrophilic aromatic substitution. Our electrophile is represented by Y plus, and our nucleophile is a benzene ring. Does that make sense? The benzene ring is the nucleophile, Y plus is the electrophile. And what you notice is that the Y simply replaces one of the hydrogens in the benzene ring. Because Y is the electrophile replaces a hydrogen and then you form a hydrogen plus. That's why this reaction is called electrophilic substitution. Because an electrophile replaces a hydrogen atom on the benzene ring. That is the general scheme. So our job here now will just be varying the nature of the electrophile. That's all we'll be doing. We'll be varying that nature. We'll be changing, we'll be using different types of electrophile and reacting it. That's basically what we'll do today. Okay. Now, the mechanism of electrophilic aromatic substitution. I don't expect you guys to know this mechanism. I don't expect you guys to memorize this mechanism, but it's just good for you to have an idea of what is happening. So I will not go into the detail of this mechanism per se, okay? But then the first step of the mechanism, it's a two-step mechanism. That's what I want you guys to remember, okay? I want you guys to remember that it's a two-step mechanism. And then the first step of the mechanism is the formation of the carbocation. Formation of the carbocation, that's the first step. And that formation of the carbocation, as usual, I always told you guys, is the slowest step. So that's the rate determining step, which is this first step here. So you form your carbocation intermediate. And I want you to take note that that carbocation intermediate is very stable because it can undergo resonance. Okay, the carbocation intermediate is very stable because it can undergo resonance. Then the second step of the reaction is the removal of the hydrogen or removal of a proton. Removal of H plus to form your final product. And that process is fast. So it's a two-step mechanism. And for a two-step mechanism, that's how the reaction coordinate will look like. Two-step means you have two transition states. You have the first transition state and you have the second transition state. And you can notice that the first transition state is high in energy compared to the second transition state, making the first transition state your rate determining step of the reaction. And that first step is the formation of the carbocation. Okay. Now, the first reaction that we'll be studying today will be the bromination and chlorination of benzene. Okay. So for the bromination of benzene, you react bromine and the benzene ring in the presence, react bromine and the benzene ring in the presence of iron bromide. This is iron bromide. And that leads to your substituted product and the formation of HBr as byproduct. Same thing with the chlorination of the benzene. You have your chlorine. So in this case, you have your chlorine reacting with the benzene ring in the presence of iron chloride to form your final product, chlorobenzene. And so you want to notice here that the formation of chlorobenzene and bromobenzene require the use of a catalyst. And that catalyst is a Lewis acid. In this case, the catalyst used are iron bromide and iron chloride. Those are the catalysts. You remember the job of a catalyst in the reaction. A catalyst helps to speed the reaction. So that's the purpose of the iron chloride. Okay, and this is simply because chlorine and bromine are not very reactive. And so we use the catalyst to activate the chlorine and the bromine to make them become reactive. That's the purpose of using the catalyst. And the next slide is simply giving us a mechanism of activation. How is the bromine activated in order to react with the benzene ring? So there is an interaction between our bromine molecule and the catalyst that creates this intermediate, and that intermediate now makes this bromine atom a very good nucleophile. I hope you guys see that. And the reaction, this was the nucleophile, but it wasn't the best of the nucleophiles. But when it interacts with the catalyst, it now transforms that bromine and makes the bromine a very good electrophile. And being a good electrophile, it can easily react with the benzene ring now. Okay. So usually we refer to this particular step in the mechanism as the generation of the electrophile. And this is something that you'll be seeing more often in the reaction of the benzene. The electrophile are sometimes not easily accessible, and sometimes you always need to generate the electrophile. You always need to generate it using a Lewis acid, and that's what we'll be saying regularly. Okay, and one of your job is to know how to generate that electrophile in order to cause the reaction to happen. Okay, and so once the electrophile is generated, then you can have your mechanism, which is very similar to what we've done above. You have your benzene ring acting as a nucleophile, reacting with your activated electrophile. Remember, this is the bromination. It is reacting with your activated electrophile to form your carbocation intermediate that collapses now to generate your benzene ring and blah, blah, blah. These are all byproduct. But notice that in your byproduct, you are regenerating your catalyst that you started with at the beginning. Okay, and so the steps are summarized for you here. First step, electrophile adds to the benzene ring. Then the second step of the mechanism, a base removes a proton to form the bonded electrophile to form the carbon bonded to the electrophile. Does that make sense? It's the same mechanism with chlorination. You have your benzene ring reacting with the activated chlorination, with the activated electrophile. This is activated because it's already in interaction with the catalyst. And then you form your intermediate. Then the intermediate now collapse to give you your final product. And notice again that we have reiterated our catalyst. Does that make sense? And so to prepare the catalyst for the chlorination, I will not really want you guys to worry about this, okay? Don't worry about this one. How to prepare a catalyst. Seriously, this is not very interesting. Now, we've talked about chlorination, we've talked about bromination. The next thing we'll look at is the iodination, how to add iodine to a benzene ring. Unlike bromination and chlorination, where we need a Lewis acid, in the iodination, we simply use a peroxide, hydrochloric, and sulfuric acid. Okay, so if you have your iodine molecule with a benzene ring in the presence of a peroxide, hydrogen peroxide, this is what we call hydrogen peroxide. In the presence of hydrogen peroxide and sulfuric acid, then you are able to form your iodination product. Like I said, all reaction always goes through the generation of the electrophile. And so to generate your electrophile, the iodine reacts with the peroxide and the sulfuric acid to create your I plus. And the I plus now will react with the benzene ring to give you the final product. Does that make sense? So I want you guys to be able to recognize those reactions. How do you add the bromine? How do you add a chlorine? How do you add an iodine in the molecule? You don't necessarily need to be able to draw the arrow pushing mechanism. I will never ask you to draw the arrow pushing mechanism. But again, like I always say, knowing the mechanism on your own is better because it makes you remember that reaction easily. And so once the iodine is generated, the mechanism is very similar to the other one. The first step of the mechanism, electrophilic addition, and then the second step of the mechanism, removal of the proton, which is the same as what we've been saying before. Okay, step of the mechanism, that's what we've been talking in the past. Okay. Next reaction we'll be talking about. This is reaction number 3. This is reaction number 3 we're talking about. Reaction number 3 is the nitration of benzene. So nitration of benzene is adding an NO2 group to the benzene ring. And if you noticed, in order to add the NO2 group in the benzene ring, you need 2 reagents. You need nitric acid mixed with sulfuric acid. Okay, those are the 2 acids you need in order to create a nitration. And so the mixture of these 2 acids, we call that the nitrating mixture. Okay, just like any other reaction, you have to generate your electrophile. Like I said, the first thing is always to generate the electrophile. And to generate the electrophile, your nitric acid reacts with the sulfuric acid. And so when the nitric acid reacts with the sulfuric acid, it produces what we call the nitronium ion. And so the nitronium ion is now what acts as the electrophile. Generally, we'll refer to the mixture of nitric acid and sulfuric acid as the nitrating mixture. Okay, we generally refer to this mixture as the nitrating mixture. So you mix nitric acid and sulfuric acid together, and then you form the nitronium. And from your nitronium ion, now you're able now to do your reaction. So the nitration, in this nitration, sulfuric acid is protonated by a nitric acid. Sulfuric acid is protonated by nitric acid, and then you have a loss of a water molecule from nitric acid to give you the nitronium ion. Once the nitronium ion is generated, the mechanism is very similar to what we know. You have your nitronium ion. The nitronium ion now react with the benzene. Please take note of the direction of the arrow, okay? If you want to do that in the future. The nitronium ion now react with the benzene ring, generate your carbocation intermediate, and then forms your final product. It's the same step: electrophilation, then removal of the proton. Okay. Reaction number 4. Reaction number 4 is sulfonation of benzene. That's reaction number 4. Sulfonation of benzene. And in the sulfonation of benzene, all you need to do is react your benzene ring with sulfuric acid. Okay. Once you react the benzene ring with the sulfonic acid, you will add the sulfonyl group to the benzene ring. That's all about sulfonation. And so you notice that with sulfonation, one thing you notice with sulfonation that is different from the other reactions that we've talked about so far is the use of heat. Okay. So that triangle means heat. So you need to heat the reaction. That's one thing you notice that we didn't do with the other one. And then secondly, sulfonation reaction is reversible. That's what makes sulfonation slightly different from the other one. So it's a reversible reaction. Okay. So take note of those differences. Now, just like every other reaction we've done, the first step is how do we generate the electrophile? And to generate the electrophile in sulfonation reaction, the sulfuric acid interact with each other. So the 2 sulfuric acid molecules interact with each other and then create the sulfonium ion. Once the sulfonium ion is created, that sulfonium ion now reacts with your benzene ring to create your intermediate and then the product. Again, I will repeat it again. It's the same step as any other reaction. Electrophilic addition, then removal of a proton. The only difference here is how is the electrophile generated. That's what makes the difference. How is the electrophile generated? Once you generate the electrophile, the reaction follows the same pattern. Okay. Any questions so far? If you have any question, don't hesitate to stop me. Okay. Now, the product of a sulfonation reaction. The product of a sulfonation reaction is usually what we refer to as benzene sulfonic acid. Okay. And those benzene sulfonic acid are generally strong acids. And the reason is clear, right? They are generally strong acid because if they lose the proton, they will form called the benzene sulfonate. And that benzene sulfonate is very stable. The benzene sulfonate is very stable because it can undergo resonance. Okay, and remember, if your conjugate base can undergo resonance, it means that your acid is a strong acid. And for those resonance, you can see I can have my X, my Y, and my Z here. Or I can have my X, my Y, and my Z over here. You see, those are the different resonances that can happen in here. Okay, or you can see over here a single and a double bond. So you see, you have conjugation mixed with resonance and all those kind of stuff, and it makes that conjugate base very stable. And if that conjugate base is very stable, then the acid is a strong acid. That's what we've talked about in the past. Okay, that's why benzene sulfonic acids are strong acids and very useful acid, especially in the drug industry. And because sulfonation reaction is a reversible reaction, remember I told you that at the beginning. Because sulfonation reaction is a reversible reaction, at high temperature, it will collapse to give you back your benzene ring and SO3, sulfur trioxide. Okay, at high temperature, in the presence of telluric acid, it will collapse to give you back the benzene ring and sulfur trioxide. That's the meaning of being reversible. And again, like I said, I don't really worry about this, so we shouldn't worry about the mechanism of desulfonation. All you need to remember is that sulfonation is reversible at high temperature, and that's the only electrophilic reaction that we know that is reversible. I need a question so far, guys.
Dr. Zika,
Yes.
so you said we're not required to know any of the mechanisms for any of these reactions?
Yes, I will never ask you to draw the reaction mechanism, although we are using mass chemistry. I will never ask you to show the arrow movement. But at least I want you guys to be able to know, how an electrophile is generated, or what kind of mixture or what kind of condition are necessary to generate the electrophile, because I will never give you an electrophile straightforward like that. You will always have to be able to generate it before using it.
Okay.
Dr. Zuko,
Yes.
so the sulfonation of benzene, that's the only mechanism that's reversible?
That's the only mechanism that's reversible that we're seeing here.
Okay, thank you.
Yes. Okay. We will proceed to next one. Just give me a second. I want to save this thing. The next kind of reaction we'll be talking about are a series of reactions called the Fidel-Crafts reaction. And these reactions are very important. These reactions are very important. So, Friedel-Crafts substitution. Friedel and Kraft were two scientists, okay? One was called Charles Friedel, the other one was called James Kraft. And so they created this reaction that help us to place groups onto the benzene ring. And there are two types of Friedel-Crafts reaction. There are two types of reaction. The first type is referred to as a Friedel-Crafts acylation, In the Fidecraft acylation, we simply add an acyl group to the benzene ring, and this is our acyl group. That's what we refer to the acyl group. Okay, so if you put your benzene ring over here, that will be the product of our Fidecraft acylation. And then the second type of reaction, the second type of Fidecraft reaction is an alkylation reaction. And in an alkylation reaction, you are simply adding an alkyl group. And so if I put my benzene ring here, that will usually be the product of my Fidecraft alkylation. And again, I will emphasize, like any other reaction of the benzene, the most important thing is the generation of the electrophile. Okay, generation of the electrophile. And in the Fidecraft acylation and acylation reaction, for example, the one we're using here, we're using a Lewis acid as our catalyst, and the job of the Lewis acid is to create the electrophile. Okay, the job of the Lewis acid is to create an electrophile. And so for a Fidecraft acylation, we can use an acyl chloride or an acid anhydride. This is an example of an acyl chloride, and this is an example of an acid anhydride. And in that acylation, only the part colored in yellow or in green is what is added to our benzene ring. Okay, same thing with your anhydride. Only this portion of the anhydride is added to the benzene ring. Take note, like I said, you need a catalyst. And you can already imagine, I guess you guys can already imagine what will be on my next slide, right? What will be on the next slide? I need someone to tell me what will be on my next slide.
The mechanisms.
Not just the mechanism, more to be more precise. I want you to be more precise. Yeah, someone is saying it. I didn't hear you. Say it again.
Making the electrophile.
Making the electrophile. Yes, that will be the next thing that will appear on my slide. Making the electrophile. So let's go to the next slide and make the electrophile. Oops. No, this is not what I wanted to do. Yes, this is what I wanted to do. So the next thing will be making the electrophile or mechanism, the Fidecraft acylation. Yeah, it dealt with me. No, this is what I wanted also to see. Yes, here. So we have our acyl chloride that reacts with our catalyst, and so we now create our acylium ion. So the acylium ion is the electrophile. Does that make sense? So once we make the electrophile, then the electrophile react as usual. Electrophilic addition, then removal of the proton to give us the final product. Okay, electrophilic addition, then removal of product to give, removal of the proton to give us the final product. That's basically the Fidecraft acylation. Okay. Now, in the Fidecraft acylation, like I said, the aluminum chloride react with the product of the Fidecraft acylation sometimes. Our aluminum chloride can react with the product of the acylation. And so, in order to make sure the reaction proceeds cleanly, more than one equivalent of the aluminum chloride is usually used. Okay, because the aluminum chloride forms a complex with a carbonyl group in the product. But once water is added to the reaction product, it liberates the aluminum chloride. So the aluminum chloride phase of the product. This is just for your information. I will never ask you what happens to the aluminum chloride or stuff like that. Okay. Now, benzaldehydes cannot be made by the Fidecraft reaction. Remember, this is what we refer to as benzaldehyde. So benzene with the aldehyde group. That's what we refer to as the benzaldehyde. They cannot be made by the Fidecraft reaction because the acyl chloride or the acyl chloride or formyl chloride is very unstable. Okay, and so it has to be made somehow. So most benzaldehyde are simply used by the reaction of a carbon monoxide and hydrochloric acid under high pressure. Once we form our formyl chloride that's very unstable, we'll quickly react that with the benzene ring to give us a benzaldehyde. Okay, so usually we refer to as the formyl chloride is generated in situ. Okay, we say it is generated in situ, meaning that it is generated within the reaction. And that reaction is usually referred to as the Gatterman-Koch reaction. It's not. It will just give you the names in order to honor the guys that were the first to do this reaction. I don't really expect you guys to memorize all those names. Okay, but if you notice, that reaction is not very different from the Fidecraft reaction because it also uses aluminum chloride. Now, the next type of Fidecraft reaction we'll be talking about will be the alkylation, where you use an alkyl group. Okay, and so for your Fidecraft alkylation, you use an alkyl chloride or an alkyl halide. For the Fidecraft reaction, you use an alkyl halide. So you react an alkyl halide with a benzene ring, and you form the benzene with the alkyl halide. Just like the Fidecraft acylation, you need the presence of a catalyst, and the catalyst in this case is aluminum chloride. Okay, and just like any other reaction, the next thing you want to do is, how do I generate my electrophile? And to generate the electrophile, your alkyl halide interact with the catalyst, and then you form your carbocation. You form your carbocation. And once the carbocation is generated, the mechanism is the same. Your carbocation reacts with the benzene ring, creates an intermediate, and then you have a final product. Two-step mechanism like every other one. Now, can someone see the problem with this reaction? Can someone see the problem with this reaction? Andre, do you see the problem with this reaction? We have a carbocation. Our electrophile is a carbocation.
It can rearrange.
It can rearrange. Thank you, sir. Okay, whenever you have a carbocation, you need to be careful. Sometimes you will create a carbocation, but the product will not be what you were expecting because the carbocation can rearrange. Does that make sense? We'll look at some example in the future. I'm very sure about that. Now, the alkylated benzene product is more reactive than benzene itself, so you need to be careful. Therefore, a large excess of benzene is needed to avoid multiple reaction. Okay, this is usually good when you're doing stuff in the lab. These are the things that you need to know in the lab. Large excess. Just like what Andre said in the beginning. You remember what the answer that Andre told us earlier on. Andre said the carbocation can rearrange. Okay, and because the cation can rearrange, it can lead to undesired product. So in your mind, you were like, okay, this is a product I want to form. And then you realize that you instead form a different type of product simply because of that rearrangement. For example, if you have your benzene ring reacting with 1, 2, 3, 4, 5, with 6, 5, 1, 2, 3, 4, with butyl chloride. This is butyl chloride or chlorobutane. Let me put it that way. Let me call it this way. If you have a benzene ring reacting with chlorobutane, okay, their intention maybe is to produce this compound here. That's your intention. That's what you are planning to produce. But the problem is that when the chlorobutane interact with aluminum chloride to generate your carbocation, this is the carbocation that will be formed. That will be your carbocation. What type of carbocation it is? Primary. We have a primary carbocation, and we all know that primary carbocation are not good. And so that carbocation undergoes a 1,2 hydra shift and then generate a secondary carbocation, which is more stable. And that more stable secondary carbocation is the one that goes in and acts as the electrophile now. It now acts as the electrophile and it leads to the formation of this product. So this is the product you will observe and you will not see this product. That's the problem with a rearrangement. Question. Let me call this product A and let me call this product B. My question is, how then, if I want to synthesize A, what should I do? How do I synthesize A? Because if I do it this way, I will always have a rearrangement and it will give me B. So the question is, I need to synthesize A. What should I do? What should I do? Does that make sense? What should I do? Let's see if we can answer that question. Okay, you urgently need to synthesize A. Maybe that A is the guy that will be curing corona. So how do I do that? How do I do that? We'll get to it. Keep that in mind. Okay. Another example where you can have a carbocation rearrangement. If you react your benzene with this molecule here, what you notice is that you will form a primary carbocation, and that primary carbocation will undergo a methyl shift to give you a tertiary carbocation. So instead of forming product A, you will end up forming product B at a high percentage, because product B is a product of a rearrangement reaction. And so again, my question remains, how do I form product A? How do I form product A if I need that? Now, like I said, primary carbocations are very unstable. So for Fide-Krapf alkylation, the mechanism are written as if the primary carbocation is formed, but technically you don't form. You don't form the primary carbocation because, like I said, they are too unstable. Okay, and so you create a fake. I will call that a pseudo. So you create a pseudo carbocation that undergoes a rearrangement to generate your pseudo. This is a pseudo secondary carbocation, and that's a pseudo primary carbocation. So technically, they are not just drawn out the way we always do that. Okay. Like I said again, I don't expect you guys to know all this mechanism, but I expect you guys to know that it will interact with the catalyst to give your carbocation, and make sure that if the carbocation can rearrange, then rearrange it. If your carbocation can rearrange, go ahead and rearrange it to give you your product. Okay. Now, the Fide-Krapf alkylation is very, very important, especially in biological systems. These are just uses of a Fide-Krapf reaction. It is used in the biosynthesis of vitamin K, basically. Okay. And over here in this Fide-Krapf reaction, this is our electrophile here. Guys, no matter how complex a structure is, the most important for you is to be able to identify the component of the structure. Okay. I feel like there's somebody with the. Let me see. Like I said, the most important is for you to be able to identify the portion of your molecule. Okay, so this is my electrophile, and so you can see how the electrophile is here. So once you've generated the electrophile, this whole molecule is acting like the benzene ring because it is aromatic. Anything that's aromatic behaves exactly like benzene in terms of reactivity, and so it now connects to that to create your carbocation intermediate, and then you remove the proton to now do that under several steps, and then you form your vitamin K. Okay, those are the things that those who be doing food chemistry and be synthesizing vitamins that will be used under the counter for you guys to take as vitamin supplement. Those are the kind of reactions they spend their time doing and producing those vitamin supplements. Remember my question. You remember the question I asked you before? This question. How do I make A? How do I make A? Now, if I want to make A, I will proceed through a secondary road. I will do something tricky. The first thing I want to do is I will do a Fide-Krapf acylation. Okay. If I want to make A, the first thing I will do is a Fide-Krapf acylation. Once I form my acyl substituted benzene, the next thing I do is reaction with hydrogen. And this reaction with hydrogen is called reduction. Does that make sense? So the first step of my reaction, if I want to make A, the first step of the reaction is an acylation followed by a reduction. And then you see that I clearly formed the product I wanted. This is the product I wanted. So that's how you that's what you do in order to synthesize the product by avoiding a rearrangement of the carbocation. Okay. First step, Fidecap acylation followed by reduction of the carbonyl. Does that make sense? Those are the two steps. So that's how I will make my product A, by avoiding that way. Okay. Now, in terms of reduction, there are different ways you can do your reduction. This particular reduction here is called a catalytic hydrogenation. That's the way the reduction is called here. It's called a catalytic hydrogenation. Okay. Reduction of an SI substituted benzene. You can do that by catalytic hydrogenation, or you can do it by another way called Wolff-Kishner reduction. You can do it using the Wolff-Kishner reduction. And in that Wolff-Kishner reduction, you use hydrazine in the presence of hydroxide. This guy here is called hydrazine. You use hydrazine in the presence of hydroxide. That reduction is called the Wolff-Kishner. That's our Wolff-Kishner reaction. And so you do that reduction. And this reduction, this Wolff-Kishner reduction, is a basic reduction, meaning you are doing the reduction under basic condition using a hydroxide. Okay, you're doing the reduction under basic condition. And if I can do a reduction under basic condition, then chances are that I can also do a reduction under acidic condition. The Wolff-Kishner reaction mechanism, I don't expect you guys to know it. I don't expect you guys to know it. Oh, hold on, there's one other reduction I wanted to talk about, but they haven't mentioned it here. Okay, they haven't mentioned that reduction here, so that's fine, we'll skip it. Are we good up to this point, guys? I know we're having a lot of material. Remember, I said today we'll only be looking at the reactions. Okay, now, once you are able to form your substituted benzene, that substituted benzene can easily react because this carbon atom here, the first carbon atom connected to the benzene is particularly reactive. We refer to that carbon atom as a benzylic carbon. Okay, we call that the benzylic carbon. That carbon atom is particularly reactive, so you can undergo reaction, substitution reaction with that carbon. So if you react that in the presence of benzene and light, you can easily brominate that particular carbon. If you react that using NBS, NBS stands for N-bromosuccinimide, succinamide. That's the meaning of NBS. This is the B, this is the N, that's the B, and that's the S. So that's what NBS stands for, N-bromosuccinimide. If you use N-bromosuccinimide, you can also brominate that carbon, okay? So bromine will selectively substitute the benzylic hydrogen in a radical substitution reaction. So we've talked about radical reaction when we're doing 301. So if you use NBS in the presence of peroxide or bromine in the presence of a UV light, you'll be able to undergo those substitution pretty easily. Okay. Other substitution at the benzylic position. Once the bromine is connected to the benzylic position, you can now carry out SN2 reaction, similar to what we've done in the past. You can now use your nucleophile to kick out the bromine in an SN2 reaction. Your nucleophile can be a hydroxide, it can be a cyanide, or it can be ammonia. Okay, and so that will lead to the formation of your different products. These are substitution reactions similar to what we've done in the past. This is just a reminder. Yes, I can see a hand is raised. Who is that?
Dr. Zico.
Yes.
With this information you're giving us, are we just expected to know it like in the back of our heads, or do you want us to know like this whole process?
I want you guys to be able to do it because in an exam I can easily ask you, okay, for example, a typical question. We'll do some example in here. A typical question in the exam, I can easily draw my benzene ring, and then I will now draw this and probably draw something like that, and then make this and make this and ask you to give me what the product will be. Does that make sense? And then
Okay.
I'll ask you to draw the structure of the product. Or I will draw a couple of products and ask you to choose the correct product among them. Does that make sense?
Yeah, okay, so that being the case, can you like backtrack and go over this again? Because you kind of lost me. You're kind of going a little bit fast.
Uh, Backtracking, it will be a little bit hard to do. I will post the video and you'll be able to watch it. Because if we backtrack, we will not be able to move forward. That's why I'm recording the session, so that you can always go back and review it.
Okay.
Mm. Another thing we can do is that once we have the bromine connected to the benzylic position, we can always undergo an elimination reaction, which is an E2 reaction, what we've seen in the past. You can easily do the E2 reaction to form your double bond over here. So that elimination process can happen. And so basically what I want to let you guys know is that once you've been able to form your brominated substituted benzene, any type of reaction can happen to it, similar to what we've seen in the past. And this is a time that you have to remember all those reactions. That's the problem with organic chemistry. What you learn in chapter 1 is not only meant for chapter 1. You will use it throughout the course. So any information you've learned before will be useful. That's the thing. That's what makes organic chemistry a little bit special. Okay. You don't just throw information. Okay. And again, these are the things that we'll barely be able to see. If you have your substituted product, you can undergo a reduction to form your alkyl bromide. If you have the cyanide over there, you can undergo a substitution to form that other product. This is called, all of these are catalytic hydrogenation. Those are all catalytic hydrogenation. Those are all reduction reaction. Those are all reduction reaction. Okay. Another reduction reaction that benzene ring can undergo is at high temperature. If you heat the benzene ring in the presence of hydrogen and nickel at very high temperature and pressure, you will reduce that benzene ring to a cyclohexane ring. Okay, you will reduce the benzene ring to a cyclohexane ring. Alkylated benzene can easily be oxidized. Oxidation is the reverse of reduction. Oxidation is addition of oxygen. And so when you have an alkylated benzene and you use an oxidizing agent, for example, we're using chromic acid here, the oxidizing agent will transform the benzene into benzoic acid. It transforms that to a benzoic acid. This is a carboxylic acid. Okay. Now, no matter what the arrow group is, no matter the nature of the arrow group, no matter how big the arrow group is, once you have that arrow group there in the presence of an oxidizing agent, it transforms it to a benzoic acid. If you have two arrow groups, then it gives you dibenzoic acid. Okay. Now, what is the key here? All you need is that your benzylic carbon must have at least one hydrogen connected to it. Once your benzylic carbon has at least one hydrogen connected to it, it will always be oxidized to a benzoic acid. Always oxidized to a benzoic acid. Okay. But if your benzylic carbon does not have a hydrogen connected to it, there will be no oxidation. Does that make sense? Look at the slides where we have oxidation. We have at least one hydrogen on the benzylic carbon. But if you don't have a benzylic hydrogen, then there is no oxidation. That's what I want you guys to remember. No benzylic, no oxidation. Now, another reduction reaction. Once you have your nitro product from the nitration reaction, remember, this nitro product was formed from the nitration reaction, meaning if you have your benzene ring, you react the benzene in the presence of nitric acid and phosphoric acid. You will form your nitro product. Now, if you have the nitro product, you now undergo a reduction, and that reduction leads to formation of an amide. So, this guy is called aniline. Trinity, you know what aniline is, right? You've used that in the past. I think Trinity and Kelly, you've used aniline in the past. So if you reduce your nitro product, you form aniline. Again, all I want you guys is to be able to know what are the products that will be formed. The mechanism, I don't really care much about it here. Okay, I don't really care much about it here. Question, guys. If you don't have questions, then no.
Okay, Dr. Zika,
Yes.
just for clarification, we're expected to know, for the reactions, we're expected to know the, I guess, intermediates used and the product formed. And then for that, I guess what you just did, I don't really know what it was, to be honest with you, but we're expected to know not the mechanism per se, but like the process.
Yes, like if I give you this and that, you at least need to tell me that this is what will be formed. Or if I give you the benzene and the reagent, you should be able to tell me that this is the product that will be formed. Or if I give you the product, you need to be able to tell me that these are the reagents I will need. Does that make sense?
To an extent.
I have a poll open here, guys. I'm waiting on 12 people, guys. In 5, 4, 3, 2, 1. Okay, I will I will stop it this way. So those who participated, I will assume they're the ones that are there. So those are the responses. A good number of you guys had it correct. The answer will be E. And let's see why the answer is E. Halogenation. Halogenation has to do with the addition of bromine, chlorine, and iodine. And we've talked about it. Yes. So that's an electrophilic aromatic substitution. Nitration has to do with the addition of the NO2 group. Okay. And yes, that's an aromatic substitution. By the way, for halogenation, you will need a Lewis acid, FeX3, where X could be chlorine or bromine. For nitration, you will need a nitrating mixture. And the nitrating mixture is nitric acid mixed with sulfuric acid. Does that make sense? That's how you will generate your NO2 plus. That's how you generate the NO2 plus. Now, sulfonation. Sulfonation is the addition of the SO3H group to the benzene ring. And for sulfonation, all you need to do is react the benzene ring in the presence of sulfuric acid. Okay? And we've talked about the Fiedecraft alkylation and Fiedecraft acylation. And in this group, in this case, you will need an alkyl group or you will need an acyl group. Or you need an acyl group in the presence of aluminum chloride, which is your catalyst. Aluminum chloride is a catalyst. And in this reaction, we said you need to be careful when you are doing the alkylation because your carbocation can rearrange. Okay? And so all of these reactions are example of electrophilic aromatic substitution. Does that make sense? So this question is basically a summary of what you and I have discussed today. That's basically a summary of what we've discussed. So Jasmine, what I want you to do is, these are the four main types of reaction we've discussed today: halogenation, nitration, sulfonation, and the Fiedecraft reaction, both acylation and alkylation. What I want you to do is have your summary page. You draw the benzene ring, how it reacts with bromine in the presence of the ion bromide to give the product. Draw the benzene ring in the presence of nitric acid and sulfuric acid, then it gives you the product with NO2, and so on and so forth. That's basically what I want you guys to be able to remember for today. Those different reactions, reactant and product, reactant and product. Does that make sense?
Yeah. But I have a question, Dr. Zico.
Yes.
So, even though sulfonation is the only one that's reversible and uses heat, it still undergoes the electrophilic aromatic substitution.
Yes, it's still on the go. But just
So,
that sometimes it can now reverse and give you back your starting material.
okay, so with that substitution, we're more so looking at how the electrophile is formed.
Yeah, well, to how the electrophile form, remember we said it interact is two molecules of sulfuric acid that interact with each other. We said two molecules of sulfuric acid interact with each other. That's my next polling question. And let me open it for everyone. Yes. So which of the following statement is not true about the sulfonation of benzene? I need 8 more responses. Which of the following is not true? Jade, you haven't responded, Jade. I need your response. Same thing with Alexandra. Alexandra, can you turn off your mic, please? Okay, I will show the result. Yeah, a good chunk of you guys have it correct. A good number of you have it correct. So let's look at it. Which of the following statement is not true about sulfonation of benzene? Heating sulfuric acid leads to the formation of that, which is true, right? This is true because that's the generation of the electrophile. That's how we generate the electrophile, by heating sulfuric acid. Okay. It says sulfonation is irreversible. I don't believe. I don't believe. We said in this class that it is one of the guys that is reversible. Okay. So that's the guy that's reversible. C says sulfonation occurred through an electrophilic aromatic substitution. I believe that's true. Okay. The rate limiting step is formation of a resonance stabilized carbocation intermediate. Yes, that's also true. All of these statements are true. No, I don't believe. Yeah, you see, I hate answering this kind of question. Normally, somebody that choose B or E will be correct because it says all of these statements are true, which is not true. Okay, so but the best choice, okay, the best choice in a test of knowledge, I would say B is the answer I will go for. B will be the best answer. Okay, this is another type of question I can ask you guys in the exam. Which set of reagents should be used to prepare N-propyl benzene? This is a structure of N-propyl benzene. So which of these reagents will be used in order to prepare N-propyl benzene? Let me open the poll for you guys. While I'm working on the poll, you guys should be thinking about the answer already. Ready? You guys can start answering. I will think aloud. Those who are selecting A, I have a problem with you guys. So think again about your choices. For all those selecting A, I have a problem with you guys. Think about it again. Yeah, it's okay. It's okay. Just go ahead and choose something else than A because I already told you that if you are selecting A, there's something wrong with that. It's okay. That's why we're here. That's why we're doing this exercise. So at the end, you'll be able to know the answer. Okay, I'll close the poll. I have 4 people that never answer my polling. And those guys, I'm very sure they're probably sleep somewhere right now. They just come in, they connect, and then they go back to bed. Okay, so let's look at a solution. Now, I had a problem with those who said A simply because when you look at A, you will form your carbocation, and that carbocation will rearrange. Okay, with A, this is the initial carbocation that you will form, but that carbocation will rearrange to give you a secondary carbocation. And if it rearrange to give you the secondary carbocation, then A will give you this product, not what we need. Does that make sense with the A? So that's why I said A, you should be careful. Okay. Now, B, we haven't seen a reaction like that with B, reacting a benzene with a double bond. We have never seen it in this class. So B can never be correct. I've never talked about B. Okay. Now, D, there's a problem with D. Again, I've never talked about a reaction of the benzene ring with the presence of an alcohol. I have never talked about that. So D will never be correct. Same thing, same reason why B is not correct. E also is not correct. Okay, E also is not correct. So the only correct answer here will be C. C will be my correct answer. C here means that you have a benzene ring in C, and then you react it with this acyl chloride. That acyl chloride is CH3, CH2, carbon double bond oxygen, chlorine, in the presence of aluminum chloride. When you react that, you will form this product. But then the second set of product, these guys here, remember what this is, okay? This is hydrazine. You remember? I mentioned it in this class. This is hydrazine in the presence of a hydroxide. And so if you react this with hydrazine in the presence of hydroxide, you will do a reduction. So this is a reduction process, and you form your product. Does that make sense? You form a reduction and you form your product. So Jasmine, you've seen a little bit how the questions can be asked here in this section. And based on this kind of question, you should know, you should develop a studying strategy. Because that's basically how I'm asking you a question whenever it comes to this section. Okay?
Dr. Zico, this is a lot. And that was kind
I
of
know. I know that is really a lot.
That's all happening at once. This one whole reaction.
No, it's a two-step reaction. That's why it says 1 and 2.
But then it has
So
3. What's
no,
that 3?
yeah, and three whatsoever. It's a three-step reaction. It means you first do the first one, then you do the second one, and then you do the third one. All of them, 1, 2, 3.
Dr. Zico, please don't put this on the test.
Say that again.
Please don't put this on the test.
Uh,
This was
uh,
confusing.
well, I'm sorry. You probably have it in the test.
Oh my gosh.
You'll definitely
When
have
is
it
the
on
test?
the test. You'll definitely see this on the test.
Can we
So,
do more practice like this then?
say that again.
Can we do more practice like this? 'Cause I really didn't know how to approach the question.
Don't worry. Oh, wait. So I have a lot of questions here. I have
Everyone's just saying that this was a lot and we're all confused and concerned and worried about this exam.
When is the test, Dr. Zico?
say that again.
When is the test?
The test is on the 3rd.
Okay.
What time?
We haven't decided on the time yet. So, but you guys will have to take the test all at the same time.
Do y'all know how the test is gonna be set up or no?
Yes, it will be exactly like your homework, like the homework you guys do on mastering chemistry. My intention is to give you guys like a practice test on mastering chemistry sometime next week.
So it won't be like the regular test at all. Will it still have like a reading section, multiple choice, and open ended or no?
I don't know, it will be a little bit different. It will be a little bit
Oh,
different. That's why we'll give you a practice test next week. That's why I will set the practice test on mastering chemistry next week for you guys to have an idea of what the test will be.
Dr. Zico, someone asked about is chapter 8 and 18 still due to tomorrow?
No, they'll be due on the day of the test.
Okay.
How can we strategize for this type of questions? Oh God. Yeah. I knew we were entering a zone of turbulence. See, what I would really say is if we can have flashcards that tells us reagent and their product, I think that will be useful. Coming up with some flashcards will be a good way of looking at things. Like I said again, the mechanisms, I don't really care about the mechanisms. We've looked at 4 types of reactions, and those 4 types of reactions are the reaction I expect you guys to know. I expect you guys to know all those 4. Those are the only 4 types of reactions I expect you guys to know. Now, some of them now you'll be able to do oxidation, some of them you'll be able to do reduction. Okay. It might seem confusing probably because it's the first time you guys are having this information. I will really, really highly recommend you guys to probably review this video or go back to your textbook. And then I will be having problem solving sessions. We'll be having problem solving session. At least next Thursday before the test, it will be a Thursday for problem solving. That one I'm very certain about it. We'll most likely finish this chapter on Tuesday. Okay. Now, today I have a lab. We have a lab at 2 o'clock. And it will not be a long lab because I will basically just show you guys how to obtain articles from the library and online, and that's it. But after the lab, I will stay again and solve some problems. So those who want to stay and solve some problems with me are welcome. Those who are not in my lab group but want to be present in the problem solving session, what I will do is I will share the link to my lab class on Blackboard. I will share this link. All you need to is click on the link and then you'll be connected to the lab class. So you'll be able to attend the problem solving session if you want to. Okay. I highly recommend you guys to do that. Like I said, the best way to understand this thing is to solve as many problems as possible. So after the lab, I will do at least an hour or so of problem solving, similar to what we did on Tuesday. And I can imagine from what we did on Tuesday, a lot of people were comfortable with whatever we're doing. By the way, the class is over. If you want to leave, you are free to leave. Okay, the class is over.
Dr. Zico, can you,
Yes, I'm
um,
listening to the question.
as far as lab and keys and money is concerned, how is that gonna work?